Welcome to the first week of Calculus 2 course. In Calculus 1, we already learned how to take limits, how to calculate derivatives of different functions, and some basic integrals. In order for us to successfully integrate a function in Calculus 2, we have to be able to do one of the three things. We can either look up an integral if we have access to the formula sheet, or we have to recall the basic integral, so just relying on our memory, or we have to use one of the integration techniques. At this moment, we only know very few things that we can do. It's either algebraic manipulation or U-substitution. Similarly, we'll also learn integration rules. For example, for definite integrals, the following rules: as an integral from a to a of any function f of x is always going to be equal to 0. The order of integration, if we flip the bounds, upper and lower bound, then the sign in front of the integral is changing. Constant multiple rule is when we have a constant multiplied by a function f of x, and we can just integrate function and then multiply result by a constant. Sum and a difference rule, so the integral of the sum or a difference, sometimes easily handled when we integrating each function separately and then adding and subtracting the result. One of the important things to remember is that there is no product or quotient rule, so integral of the product of two functions is not equal to the product of integrals, and same for the quotient, it just does not work. But there is additivity rule, so if you have a definite integral from a to b and the integral of the same function from b to c, it's the same thing as integrating function f of x on the interval ac. If I have to list the most important basic integrals that we need to remember for Calculus 2, it would be the following 11 integrals. Integral of a constant, integral of a power function, integral of function 1 over x, exponential functions, integrals, and trigonometric functions, sine, cosine, secant squared, and so on. Let's solve an example. Integral of x cubed dx. This is a power function. X to the power of n, where n is equal to 3. Integral of x to the power of n is equal to x to the power n plus 1, but n is 3. 3 plus 1 is 4, divided by n plus 1, that's 4, plus constant c. We always check if the resulting antiderivative is correct one by taking the derivative of our answer with respect of x. Using a constant multiple rule, we can remove 1/4 in front of x to the fourth, then differentiate x to the fourth using the power rule, confirming that we did get the right antiderivative. Next example. Let's integrate 3 to the x dx. The only difference between example 1 and example 2 is that I changed the base from being variable and exponent being 3 to base being a constant and an exponent being a variable x. I can no longer use a power rule. I have to use an exponential function rule. Here a is equal to 3, and using integral of exponential function a to the x being equal a raised to the x divided by natural logarithm of the base, which is a equal to 3 plus constant c, we get our antiderivative. Let's check. Derivative of 3 to the x over natural log of 3, 1 over natural log of 3 is a constant, and if we use calculator, we will not know approximately what it's equal to. So we'll use constant multiple rule, which means we just need to find derivative of exponential function 3 to the x and multiply it by a constant 1 over natural logarithm of 3. Derivative of exponential function is exponential function itself times natural logarithm of base. So natural logarithm of 3 divided by natural logarithm of 3 is 1. So that's correct. We found absolutely right antiderivative for example 2. Let's look at the example number 3. Integral of x squared times sine of x cubed dx. Unfortunately here, I neither remember antiderivative, it's not listed on the table sheet that I have, so the only thing that's left is for me to try and apply one of the techniques of integration that I know from Calculus 1. One option is algebraic manipulation. Unfortunately, this will not work. This example doesn't allow us to somehow manipulate and simplify an expression, rewriting it in a way that allows me to recognize any of the useful formulas I have on the formula sheet. So the only thing that's left is a U-substitution. U-substitution here, I would like to try, is an argument of the trigonometric function. Let u equals to x cubed. If I'll do u equals to x cubed, the derivative of x cubed is 3x squared. Therefore, differential du is equal to 3x squared dx. I can multiply both sides of this equation by 1/3, giving me an equation that allows to replace x squared dx with 1/3 du. Since u is equal to x cubed, I'll replace argument for the sign with u. This gives me 1/3 sine of u du. Now this new integral is actually a lovely integral. It's listed among the formulas. This is formula number 6. Integral of sine is equal negative cosine. So since we know antiderivative, it's equal to negative cosine of u times a constant 1/3. I can go back and change variable u back to x cubed and get an antiderivative minus 1/3 cosine of x cubed plus c. Let's confirm by taking the derivative of negative 1/3 cosine of x cubed. We will use the constant multiple rule and differentiate cosine of x cubed by itself and multiply result by negative 1/3. Derivative of cosine is equal to negative sine, but we'll have to use the chain rule because the argument for the cosine is not just x, but a function of x. Therefore, we'll have to multiply by the derivative of x cubed. Derivative of x cubed is 3x squared. 3 divided by 3 is 1. So we will get exactly the same function we started with, x squared times sine of x cubed, which means that our antiderivative was calculated correctly. It is indeed minus 1/3 of cosine of x cubed. In this video so far, we looked at two things: knowing basic antiderivatives, which we did in examples 1 and 2. We also did U-substitution. The other techniques that are related to algebraic manipulation are completing a perfect square, multiplication by 1, simplifying a fraction either by doing long division or just separating it by using subtraction or addition into 2 or more fractions, factoring out constants or opening parentheses whenever needed, or using definition of absolute values. Those algebraic manipulation techniques are very useful, and we often rely on them even when we learn more complicated techniques in Calculus 2, like integration by parts or trigonometric substitution. Please work through these examples that I'm listing in a table on your own. If you have any questions, bring them in class and we'll continue conversation there.